Okay, hi everyone. My name is Cy Brand. Welcome to Pure Virtual C++ 2021. This is our second year running the conference, and last year I ran everything from my laptop, which had some difficulties. This year, hopefully everything from now will be very smooth sailing. So we are streaming to a few places today. If you're watching from YouTube, I would recommend heading over to Microsoft Learn TV, which is where we're going to be hosting our Q&A. So if you'd like to ask any questions, please go to aka.ms/learntv. If you would like to ask any questions, please do read the code of conduct, which is right underneath the chat window. It's just to make sure that everyone has a safe and fun time. Today we have 3 hours of content made up of 5 sessions. You can go onto the website to make sure to check out the schedule. And we've got content on modules, on CMake, on code analysis, a whole bunch of stuff. We also, in the last week, published a bunch of pre-conference videos to our Visual Studio YouTube channel, which you can find and watch. They will all be available after the conference as well, including all these sessions today. You'll be able to watch them on Learn TV and on YouTube. So if you miss anything today, don't worry about it. You'll be able to check it out later. With that, I'm going to move on to our first session today, which is our guest speaker, Daniela Engert. She is one of the foremost experts in C++ modules right now, and also one of the best educators, I think. So I'm super glad to have her on today to tell us about modules and the 3 secret spices. So please welcome Daniela Engert.
Hello, everybody, and welcome to my talk on the 3 secret spices of C++ modules. I'm Daniela, an electrical engineer living in Germany. I'm creating software professionally since the late 70s. I will give you a very brief overview of what modules are about and how they look like before I move on to the 3 key features that shape the functionality of modules: divisibility of names, the notion of reachability, and then linkage, or then when does the same name refer to the same thing. Modules are one of the major additions to C++ 20. They are probably the most transformative feature in the sense how we think about designing interfaces and composing software, and how they possibly help us to avoid hard-to-detect problems. Folks, I think we are just doing it wrong now. We follow the book of John Lako's book about layering software and designing large systems. We protect the library implementation from being invaded from the outside, but our poor library interface in the interface headers has not this kind of protection. Our software may tamper with the text of our library interfaces, or they may even be outright hostile to different kinds of other software without even knowing. This is not good. For technical reasons, the interface header might even need to contain implementation details of the library that are required to form the interface, but are actually not meant to be used outside of the library, like, for example, template definitions or inline functions. In some cases, even all of the library implementation is included in the interface. The interface header is then textually inserted into the translation unit of the library implementation and also into the client translation unit that consumes the library. In the C++ compilation model, boundaries exist only between translation units. Foreign code is barred only from intruding the use of the library implementation. The interface headers just do not benefit from this level of protection. The compilation of a TU starts out from a given compiler state as set up from the compile environment, like compiler flags, macro definitions, and it starts with an empty set of declarations. At the point that the library interface header is started to being processed by the compiler, the compiler state may have changed by all of the stuff the compiler has already processed so far. The compiler state at that point may be different in different translation units, giving rise to different interpretation and meaning of the literally identical C++ text in the interface header. This may lead to subtle bugs because of ODR violations, because definitions might no longer be the same in all parts of the program. Again, we are doing it wrong. At the end of the compilation process, an object file is generated and all of the compiler state with all of the collected information is simply discarded. Using the library again in a different translation unit requires compiling the same header files over and over again. That's inefficient. Quite some time ago, at about the turn of the century, it became apparent that they need to do better. So fast forward to today, we finally can do better now. Modules change the compilation model in a way that the interface of a library is no longer textually inserted into a TU, but rather becomes a TU on its own. This shifts the protection boundary to the place between the library and the client code, right to where it belongs to be. Well, that's just a minor drawback though. We need a new communications channel that makes the contents of the interface visible to both the implementation of the library itself and also to the clients of the library. This channel is a compiled form of the interface with an equivalent representation of its contents. The compiler environment is no longer a concern. The semantical meaning of the interface is immutable. It's compiled only once, and there's therefore no place left for ODR regarding the contents of the interface. The additional artifact is called build or binary module interface, or in short, BMI. Everything in the BMI is available within the library, but only selected parts become available to the outside. We architects of the library interface decide on which entities we want to make available rather than being forced by technicalities of the language. So we can do better. The compilation of the interface starts from a known compiler state that is still untampered by unrelated C++ text. Besides the object file, the compiler will also emit the BMI with the representation of the language entities that it's collected during the compilation process. Implementations may also put some additional info about the initial compilation state into the BMI to prevent ABI problems. So compilers can do better as well, and tools too. This is the way. So how does a module look like? In the new modules world, there are not only modules, but all the already existing code that's outside of the module and need to be used again. For the sake of consistency, we call this part of the world to be the so-called global module that has no name, and the code in there follows all the traditional rules of the language as they know them. Beginning with the declaration of a module and giving it a name, we enter the module purview. The module name must be unique to each module within a program. Every entity that's declared in the purview becomes part of a new domain of names that is separate from all names in the global module and from all other modules. Be aware that this new name domain is not a namespace. Names introduced within the purview can be referred to from the inside of that module, but not from the outside. Then the module declaration has the export specifier at the beginning. It's the so-called module interface translation unit. Each module has exactly one. By prepending a declaration with an export keyword, the declaration is made available to the outside of the module. Other translation units that import this module can then refer to the exported name. Without the export keyword in the module declaration, it's a module implementation unit, which you can have as many of them as you as a library developer want to. Optionally, a module translation unit might start with a piece of code that is not part of the module purview, but rather the old-style global module. You can put your existing code or other code living in the global module here into the so-called global module fragment. This code can then be used as usual from within the module purview. Modules may also import other modules, either as a non-exported implementation detail, or they may even become an integral part of the module interface by re-exporting their interface. You cannot see the provenance of the entities that a module exports. The composition of a module interface is totally hidden. There's actually a variety of module translation unit types besides the primary module interface and the module implementation units. Each of them has a unique set of properties and features. You can pick appropriate types to compose a module. Header module units are special. They have no name, no architected interface, and even maintained other translation units by leaking preprocessor macros into them. So how do modules achieve their stated goals? The first part of the answer is related to names and their visibility. Visibility is probably quite well known to us so far. The C++ standard says that a name is visible when it's not hidden. That's only partially helpful. So basically, a name is visible when it can be found during name lookup. But before that, a name needs to be introduced by a declaration in the first place. And this must happen in this same translation unit. Compilers never look into other translation units. This seems obvious and totally familiar to us because these are the C++ rules, but other languages may have different rules. So the visibility of a named entity depends upon if that name is declared within the translation unit before it's being referred to, and if the programmer uses an appropriate lookup algorithm that is capable of finding a name in the scope of its declaration from the scope that a name is being looked up from. Otherwise, a name is invisible at the point of lookup, but it may still be visible from a different point of lookup. If we perform name lookup for entities at class scope, the rules are a little bit less restricted in case of types of dependent types in templates, or if the names are referred to while still being in the definition of a class body. In these cases, names can be referred to even before they are defined. The lookup of these yet unintroduced names is deferred until after the names are actually introduced. Sometimes it takes different kinds of lookup algorithms to find a name. Maybe a name in a sibling namespace or in a namespace, in an outer namespace, that a name of an entity of the same name is also declared at a namespace that is nearer to the point of lookup. Or in the case that you need an RDL, argument-dependent lookup to find an entity which are so-called hidden friends. These hidden friends are friend functions that are declared at class, in the class body, but are not part of the class, but rather than are technically living in the namespace that surrounds the class. And it can be even weirder than that. We can define classes within a function body that returns instances of these classes by return type deductions without even mentioning the name in the declaration of the function. The returned object can be used as usual, even though the name of the return type is totally invisible outside of the function. The compiler still has full knowledge of the type of invisible name though, because it can reach into its definition. It has compiled the definition in the function body and returned this information. So, an entity being invisible does not imply it to be unknown. So far, TUs erect barriers between them that make names declared in different translation units totally invisible. Modules extend visibility across translation unit boundaries by passing names declared in the module interface translation unit through the BMI into other translation units that imported BMI, similar to wormholes in the universe. Remember, visibility is only about names of entities to make them available for name lookup. If a module translation unit imports a BMI that's compiled from another translation unit of the same module, all names declared in that other translation units become visible. By importing the BMI, these names are introduced into the translation unit as if they were introduced by compiling the declarations themselves. Marking an entity in the primary module interface as exported, the names of only those exported entities can be introduced into TUs outside of the module. All other non-exported names in the BMI remain invisible. So, exported names become visible everywhere. Non-exported names become visible only within the module itself. So it's you, the library developer, who decides which names in the interface become visible and which names remain totally hidden outside of the module. So far, we've hardly made a distinction between the visibility of a named entity and the knowledge of other properties of that entity. We have seen one example where was a disconnect between visibility and the ability of the compiler to reach into the definition. This notion of reachability of declarations and properties is separate from and orthogonal to the notion of visibility. This distinction hardly ever bothered us so far. In the traditional world, the compiler knows everything about every declaration in the translation unit as soon as it has compiled it. And this is the case in every translation unit in the traditional world. But now, reachability becomes important in the modules world. BMIs compiled from module interfaces do not only act as a tunnel to transport names to make them visible, their second duty is to make declarations in the module become reachable when necessary. In this example here, the module mod imports another module stuff as implementation detail to use an exported class as member variable in class S. This class is not exported from module mod, but returned from the exported function foo. Class S has a member function what that returns the result of calling member function message on its member variable, without ever mentioning the name of that return type. So far, importing another module forms a dependency on that other module. Its BMI must be available for compilation. But there are more dependencies. The non-exported class S uses a non-exported type from another module as member variable. Struct S has a member function that uses this member variable in its definition. Functions return types that are either explicitly named or implicitly inferred without mentioning their names. At least some knowledge about these entities must be available at compile time to give meaning to the code. When the translation unit on the bottom imports the interface of module mod, only the name of the exported function foo is visible. Nevertheless, the compiler knows enough about the properties of the object that's returned from foo. It has a member function what, and the result type of that member function has certain properties that can be checked for at compile time and can be used at runtime. Let's look at the module stuff that was imported into our module mod. The module exports two classes that derive from non-exported base classes. These base classes are defined within the module, and one of them uses type string from the standard library as a return type of member function message. Remember, this member function was used in the member function what of class S defined in the previous module. So through inheritance and return types, even more dependencies are formed that ultimately extend into the standard library. All declarations encountered along this dependency chain that are originating from exported entities of a module interface need to be available from the outside of the module, even when the name of these declarations still remain invisible. All these declarations and their properties are said to be necessarily reachable, and therefore must be part of the BMI. Other declarations outside of the dependency chain are not necessary, but may still optionally be part of the BMI and be reachable, or they may be not. Preventing these declarations from being part of the BMI is not mandated by the standard, but is implementation defined. In this example, all declarations in module stuff are necessarily reachable from its own interface, but only some of them are necessarily reachable from the interface of module mod that imports module stuff. So what are the semantic properties of declarations or definitions? Some are mandatory, some are optional, some are defaulted. Let's define a simple function that takes an int and returns an int and give that function type a name. Implicitly and by default, it has also an exception specifier, and it's living and having external C++ language linkage. We can declare a function bar of this function type and put it into a namespace and give it a different language linkage. We can give additional semantic properties to this function declaration, for example, a function name, function parameter name. It's still implicitly external. It may have an inline specifier and an attribute, and if it's a definition of this function, it also has a function body which introduces additional declarations. The function parameter might have a default parameter, a default argument, and this default argument must be of a complete type, so the class type must even have a fully defined function class body with additional declarations, properties, and names in them. Everything shown here is necessarily must be necessarily available and reachable to make use of this function bar. In the compilation model of C++, each translation unit is compiled separately and independently. The linker then puts all the pieces together and forms a final program. The ability to do so meaningfully is called linkage. It describes properties of the API like calling conventions, and it prescribes consistently applied rules of forming linker symbols from entity names. All that such that entities of the same name in different translation units result in the same linker symbols, and also in compatible calling ceremonies. The linker will then select one of possibly multiple definitions if declared legal by inline, or complain if there is more than one of them or none at all. The formation of linker symbols is augmented in the world of modules to allow for additional semantics of names declared within module purviews. In this example here, we see two different modules declaring two different non-exported functions foo that are invoked from the bodies of exported function definitions bar and bus in namespace A. The language rules demand that importing both modules into the same client translation unit causes No problems whatsoever, even though both modules declare functions of identical names in the same namespace. As members of the respective module purviews, these functions are said to be attached to their modules. Namespaces extend across translation unit boundaries, and they are therefore not attached to modules, but rather attached to the global module. In a sense, names attached to a module seem to carry kind of a scent or branding that isn't noticeable at the language level. Cat owners know what I mean. This scent is necessary to make them distinguishable when forming the program. Names attached to the global module without name don't have that scent. To do so, we say that non-exported entities have module linkage rather than external linkage. Besides that, they both are just the same. Exported entities still retain external linkage despite being attached to the module. Then the compiler forms linker symbols from entities attached to a module with either module linkage or external linkage. The scent that marks these entities as belonging to that module becomes apparent in the mangled linker symbols. Here we see names manglings by different compilers. Symbols formed from name with module linkage must be different from symbols of entities with identical names in other modules or the global modules. Therefore, they contain parts of the in their symbol that are formed from the module name. This is another instance where the module name is has actually kind of a meaning. Symbols formed from exported names may be distinguishable, but they don't have to be. So the module name may be part of the mangled symbol name, or they may not. We call this difference in linker symbol formation to be following two schools of thought in regards to module ownership. There is the so-called strong ownership model, which retains the provenance of a symbol, and the so-called weak ownership model, there the provenance is removed. Neither is better or worse by itself, it depends on the use case. For example, in the strong ownership model, identical names can be exported from multiple modules and used in separate translation units without causing linker errors. Whereas in the weak ownership model, exported names can be moved freely between modules or from headers into modules. In certain situations, the loss of provenance may cause unpleasant surprises though. Here in this particular example, an unfortunate customer buys libraries from two different OEMs. Both libraries are delivered as binary static libs with interface headers. This is typical in some industries, for example the one that I'm working in. Both of them happen to use the same library from a third party, but in different but compatible versions. The use of that third-party library is an implementation detail that is in no way exposed to us clients and is totally undetectable at the language level. This third-party library happens to be made available to both OEMs through a module with different module names, dependent on the library version. All libraries work perfectly, but the poor customer, that's possibly me, that buys these OEM libs and uses both of them in the same product might end up either as a happy camper or face the unsurmountable problem of not being able to link the problem, depending on the compilation platform. And the origin of the problem lies in the third-party module that the customer isn't even aware of, and that both OEMs refuse to accept as a defect of their library. In cases you are concerned about this divergence of behavior on different platforms, never mind. We've got ways to make this fail also on platforms that follow the strong ownership model. By explicitly giving a name either C or C++ language linkage, the name is reattached to the global module and supposedly mangles accordingly. At least MSVC does. If you need to simulate a weak ownership model with a compiler that follows the strong ownership model, you can explicitly give exported names C++ language linkage to detach them from the module. This may also come handy if you need to forward declare a name living in the global module from within the module purview. But please use this feature only if there's no better option like including a header in the global module fragment. So, to give a recap, using an interface in compiled form rather than by textual inclusion, this isolates its meaning from the compiler state at the point of use. It doesn't taint translation units unwittingly, and it reduces the chance of ODR violations. Exporting names selectively makes visibility an architectural decision rather than being technically unavoidable. The representation of declarations in a BMI and making them reachable guarantees identical interface semantics everywhere. And lastly, augmenting linker symbols with their provenance makes T-use less promiscuous. Here are some additional resources you might be interested in, and also my contact details. And with that, thank you very much for your attention.
All right, thank you so much for that, Daniel. That was a really great talk. I sure learned a lot about modules that I'll be able to use in my projects. So I hope you did too.